let's keep going. We need to talk about enhancing the performance. If you bring in some heat at a lower temperature, but the majority of the heat at a higher temperature, it degrades the overall thermal efficiency of the cycle. And basically, an ideal Rankine brings in some heat to heat that water right in here. It's heating the water just to get it up to the boiling point. And so you might say to yourself, how much heat, if I had an ideal Rankine cycle with 8 megapascal hot boiler pressure, the boiler temperature, the boiling point temperature for 8 megapascal is around 295 degrees C. If I also have a condenser pressure of 20 kilopascal, its condensation, the condenser temperature is around 60 degrees C. So I can run calculations and say, how much heat is required to take saturated liquid at 8 megapascal from around 60, yeah, it's 60.5 degrees C or 61 degrees C, up to 295 degrees C. That's a large increase. You know what? It takes around that many kilojoules per kilogram, 1,058 kilojoules per kilogram. It'll come right out of your tables. Then you ask the question, how many kilojoules is it going to take to boil at 8 megapascal to go from saturated liquid to saturated vapor? Well, it takes 1,441. Compare those two numbers. It's a lot of heat to get it up to the boiling point. See that? It's a lot of energy just to heat up that feed water. Then you say, well, how much entropy is coming into the system due to this heat transfer? Well, pick the average temperature in here. I know it's an approximation. Just take 60 and 295, add them together, divide by 2. That's some average temperature. Add 273 to get it in Kelvin, about 451 Kelvin. And so the entropy coming into the system due to heating the feed water is around 2.34 blah, blah, blah kilojoules per Kelvin. Now, you do the same thing. How much entropy comes in at that high temperature? Around 2.5. That's quite a bit of entropy coming in for both parts of the heating. You have to get rid of that entropy. Even if there are no irreversibilities, you still have to get rid of now 4.88 kilojoules per Kelvin to be transferred. And the low temperature is going to be 60 C. So you add 273 to get it in Kelvin. And you can calculate how much you have to throw away. You have to throw away 1627 kilojoules. See that? So what's the work? Well, in, out. So the work is 872 kilojoules. And you can get a good approximation of the efficiency, about 35%, 34.9. If I go run it with the tables and all the values and do the best calculation I can, I'll calculate 35.3%. The quick little hand calculation agrees with the more detailed calculation. So hopefully you'll see that this heating right here at low temperatures brings a lot of entropy in, which forces you to throw a lot more heat out, lowers the thermal efficiency. Here's a Carnot cycle. I think I showed this last time, did I not? Also, I have some values in a table. Where did those values in the table come from? But one thing I wanted to show you is how I got this value in the table using software. So I'll have this recorded. You can go through it, but I want to show it to you. So what you want to do is you want to go out to the internet, Excel in Mechanical Engineering, or Excel in ME, in the Google search. That's the fastest way to get to the University of Alabama website. You'll click on this website, or you can just type in this whole length of this website, but it's Excel in Mechanical Engineering. They have thermodynamics, heat transfer, thermal systems. Just go to the thermodynamics and come down a little bit right here, and right here, all in one, add in for thermodynamics, which includes XDeem, refrigerant 134A, and R22, and it's right here. Now, if you have a 64-bit Windows, then you have to go here. Let me quickly show you what I know about finding out what system you're running. Come down to the, what do you call this in the bottom? This Start button. Click that, then come up to the Control Panel. So in the Control Panel, look for System. Here's System. And when you click System, it'll tell you, oh, I'm running Windows 7 and 32-bit operating system. I have another one that's operating 64. We're making that big transition. A lot of people are 64. Then I download either this one or 64-bit. I'm going to download this one. Now, it puts a 1 there because I did this trying it out, make sure I was going to be able to successfully do this. But once it's there, you can click it to run. Just click Run. Will guide you through the steps to install. So it says it's ready to install. And it worked that fast, but you're not done. So now you go and start up Excel. I have 2010 on this computer, and at this point you have to locate the add-in that was put there. So under File, go to Options. How many people have done stuff like this? Go to Options under File. So right on this button, Add-ins, click Add-ins, and down here is Excel Add-ins. You want to hit the button Go. I didn't design this. There's too many clicks and feel like a rat in a maze. You're not supposed to see ThermoTables. It's not supposed to be there because you haven't added it in yet, right? But what you would do is click Browse, and you would go find your add-ins, wherever it made it. And I think it would probably do it under Computer C drive, and I think it probably put this add-in folder right there, and inside it's one full file. It's a Excel ThermoTables add-in. So this is where it just default put it. C drive, add-ins. See that? C add-ins folder. Click that, hit OK. It says it's already there. Do you want to replace it? Yeah, hit add-in, yes. Also, anybody use Solver? If you don't use Solver, you should click it and start learning what's available, right? Solver is a great tool and that's built into, but for some odd reason you have to go and tell Microsoft, yes, I'd like to use it. Okay, and then hit OK. It fires up, it says, hey, this software was funded by the National Science Foundation, thank you. And so you have to acknowledge, yep, I thank them too every time. I'll show you how to disable that little window, pop-up window. Click on a box. Click on this box, D2 or C2 or whatever it is. So click on a box, type an equal sign, and then start, like enthalpy underscore pressure temperature, and that's this type of syntax. And then if you just scroll down, you can hit Tab to finish out, or here I'm going to hit Tab to finish that one out. Now I would put in a value, let's say 8,000 kilopascal and 440 degrees C, close paren, hit Enter, and there's enthalpy. Now, if you say, I can't, come up to this function key right here. Do you see this little function button? This explains the function, right? Because it's hard to remember everything. So it'd be, it says enthalpy in kilojoules per kilogram as a function of pressure in kilopascal and temperature in degrees C and SI units. If you want English, you have to put a third argument in. You would put ENG. And you notice right away, it shows you the numeric value that if you hit return is going to come up. It's going to cough up 426.8. But it thinks that 8,000 isn't kilopascal. It thinks it's PSIA. And it thinks 440 is degrees F. And it's going to return enthalpy in units of BTUs per pound. You can still solve those problems with this software, but I recommend just, all your homework problems and exam questions, I think, not all, but most of them are going to be SI. So it's going to return 3,247 points. So you can quickly check things. Let's say I'm just lost. I think I don't remember the syntax. I just think that there's some software installed that helped me evaluate thermodynamic properties. We'll come up to the function key and then come down this button because you have to scroll down to find it. At the top, it's all the financial, date and time, math, trigonometry, statistical functions. No, go to the bottom because you added it at the bottom. And it has refrigerant 407C, refrigerant 410A, psychrometrics, moist air, global, just X-steam, steam right there, okay? So if you click on the steam, that shows you all of these. So it starts the syntax, enthalpy, and here you can click and it gives you more description of that function, right? So enthalpy is a function of pressure and quality. Enthalpy is a function of entropy and specific volume. The state principle is emphasized. Give me two, I'll give you whatever the third is, right? I'll give you the other one. But you got to come in with two. So here's pressure. There's a whole list of pressure. Saturation pressure is a function of entropy, and saturation pressure is a function of temperature. Entropy is a function of enthalpy, specific volume. You just keep going. Is this enough of them? Temperature, if you wanted to calculate temperature. Temperature sat as a function of pressure. That's a great one. T-sat is a function of pressure. I use it all the time. So how did we find that? Come down here. Oh, it's already at X-steam. And just keep scrolling, more functions you probably ever will use. That's for steam. All right? So does it work? Liquid, yes. Two-phase, yes. Superheated, yes. Supercritical, yes. Is it going to give me the same value that's in my textbook? No, but it's very close. Why not? They coded up a different algorithm, you know. It's a little variation in the datum point. Okay? We'll get to chapter 11. We'll tell you how they generated the table. You'll be amazed that the software is even that close then. Because people still are out there refining for steam. Hey, I've got a better measurement. I think pure steam has this value for enthalpy and entropy at this pressure and temperature. Great. Update the software. All right, so what I would do is do something like this. I always build it like this. State, I make a little, that's not evaluated, that's like a little comment in that cell. And then I say, oh, pressure and kilopascal, and then temperature in degrees C. This is my style. And then maybe enthalpy in kilojoules per kilogram. I like to put what I'm, as a comment, what is in that column plus the units for that. Entropy, kilojoules per kilogram Kelvin. Let's come down here. State 0, dead state. What pressure? 100 kilopascal. What temperature? 25 degrees C. Let's get the enthalpy as a function of pressure, temperature. Now, they don't put temperature, pressure. It's lost. So there's a little pattern, like this guy comes first and second for this software. Don't worry. You get used to it. Pressure, temperature, underscore, H2O, hit tab to finish it out. And then I can click this cell to go get the pressure value, put a comma, click this cell to get and then close the parent. Enter. Right? Yeah, you wish it was that easy on exams, don't you? Pressure, temperature. Whoops, I need the, back up, come down, scroll, hit tab, hit this cell, comma, this cell. In I think in the new Excel, you don't even have to close the parenthesis, just hit enter. And it says, oh, I guess you need a parenthesis there. I'll close it for you. I saved a millisecond of my life. All right, state 1, maybe it's 8,000. 8,000, come on, I can get in there. And 440. Now, the other thing is, if you select these two cells right here, see how I selected them? And then I have this little box right down there, that little black box. Go grab that little black box and drag it down. It'll take the formula and bring the formula down, true? And guess what? So this enthalpy, I figured it's the same algorithm, but I'm going to use this new value of pressure and this new value of temperature. Make sense? How many people knew that? Pretty cool. You're good. I don't know when you learned it. When did you learn it? High school? Middle school. Middle school. All right. There was something you learned in middle school. All right. And then you can do state 3. Let's say state 3 was isentropic. Well, I just bring S down like that. Whoops. Boom. And maybe it expanded from 8,000 to 20 kilopascal. And a lot of times over here, I'll put a little comment. I'll say, you know what? Really what fixes state 2 is pressure and S. Oh, for state 1, pressure and T. It's a little reminder for myself, a little note I put typically right there. And then I say, oh, I need the temperature as a function of pressure entropy for steam, right? Then I click this cell for the pressure, and I put a comma. Then I click that cell, close paren, return. There you go. Notice this H is a function of pressure entropy for that steam, pressure, comma. Now, how many people know how to do this? I just click below and then tuck it in. It's not nice, is it? I don't know why. It's so hard to click the cell. The formula equation's covering up the cell I want to insert. So I click a neighboring cell, then I kind of grab it and move it in. If you know what I'm talking about, and you can help me do that slicker, come to my office and explain it to me. But this is my clumsy way around it. Got it? Notice I want to insert right here. Let's do this. Insert a column. And let's put quality right there, because I suspect quality as a function of pressure and entropy for water. And this is my pressure value, and that's my entropy value. I suspect that that's not 100%, so it's 80.4%. So I come up here, did the percentage, then move the decimal over. There's all kinds of playing around, right, to make it look pretty. Does that help? Very good. Now let's move on, unless you have a question for me. Thank you. So you should be able to reproduce this column right here. And also, we covered the ideal Rankine. You can reproduce these values and then calculate efficiency and other things. So I did talk a little bit more in the AM class about the history of steam power and the dangers. There's a website I found. It lists all the boiler explosions and where they happened and when they happened. You can see this is around the start of the Industrial Revolution, early 1700s. And the big one that happened in just a little north of Memphis, the SS Sultana in 1865, 1,800 people dead. And there was another one in Brockton, Mass., 58 people dead, 150. If you're a burn victim with steam, you're hurting. It is brutal. Any fire, anybody, right? But steam is just like burning. It's what's going to happen. It's brutal. And that was in 1905. That was a Grover shoe factory disaster. And then you can see even more recently, they still have some explosions. The one I showed you was 2007 in Tennessee, true? That was 2007. You go back, key safety developments in steam power, all the way back to UK, the mechanical engineers back in the United Kingdom in 1847 got together and emphasized safety with steam power. And then somebody in 1855 made it to this list, ram's bottom safety valve. This engineer invented a tamper-proof safety valve. Why? Everybody knew. You boost the pressure in the boiler, you get more power out. Better for performance, right? Dangerous. It becomes a potential pop. Blows. I mean, these kill a lot of people when they have exploded. So it's very interesting that he made it to this list because he has a tamper-proof safety valve. ASME 1880, it was formed largely in response to calls for improvement in boiler safety. They came out with a boiler testing code in 1884, and then after the Brockton, they came out with the real standard, the boiler pressure vessel code, which is kind of the bedrock of all the ASME standards. And, so engineers, they initially formed to improve safety. That's the beginning of the engineering societies. Also, you'll see that the companies, where is it? They formed a boiler, here, Hartford Steam Boiler Inspection and Insurance Company. Because if you have something insured and there's a huge loss of life, the insurance company's on the hook. So they were stepping up the ratchet. If we're going to insure you, you better operate boilers safely. Otherwise, we're going to be the ones having to fork out the money when the ship goes down and people get burned and hurt. Also, there's a lot of tractor shows and stuff. It's ever seen any of these where they have old farm equipment burning fuel like wood and coal and doing things, plowing or doing mechanical work like cutting wood or it's to get the weed out. It comes out one end and then the straw the other end. Yeah, it's some name. Anyway, you could see a lot of equipment still being run by people who restore this equipment. But you know what? It's dangerous. And I remembered that about 10, 15 years ago, I remember an accident that happened. And so I'll just tell you about that accident. It was in Ohio in around 2000. Okay, so that's a few years ago. And it was this steam engine right here. It's a steam tractor, so it was actually for plowing the field. Huge, behemoth, right? And the owner plus 5 other people, or 4 other people, 5 total, were killed when that steam tractor exploded. And all they were doing was moving it. They weren't trying to show it off, and the safety valves or nothing was at fault. What was at fault? It was old. And it had some rust and had some deposits and had some erosion of the material, and it wasn't as thick as it was when it was brand new. They traced it all down. They have a full report. You can look at it too. So you can see that it was something they just underestimated how much loss of integrity for the metal that it could handle. So all the time you say, it's a metallurgical considerations that limit our pressure and temperature. It's true. It's definitely true. Okay? So there you go. This was also the report from the Tennessee plant with that boiler accident. What I liked about this one was it showed you pictures. Here is the final location of the boiler. That's not the room it started in. That's the one I showed last time. There it is, uncovered a little bit. Here is the boiler, but there's a part that was on this end. It's now gone. We'll see it in a minute. That closed it. That's kind of where it's traveled. I guess it shot that way. Part of it shot that way and went through a wall. And if people were there, they were dead, but I don't think anybody died. The other part went that way, outdoor, and blew through it. And right here, down in the ditch, steam power. It really is. You got to be careful.
You said that nobody died?
I don't think anybody died. That guy that walked out right before. Good time to go to lunch. So now, what's interesting about this report is they said, oh, look at this. Note the disconnected, oh, come on now, operating arm. Somebody disabled a feature of the boiler. And here's another picture where they're showing you. This is supposed to be connected to this. He's pointing. That's an engineer doing that. There's a whole company, there's a number of companies in San Antonio that do what they call forensic engineering. A number of good companies. And they make a lot of money. You got to be able to handle that work. Okay, the blood was this way, the splatter was that way, the decapitated or this part was over here. This is what happened. This is the baby went this way and went that way, and the knife and the bullet in the wreck and the semi and the car and the twist, and they went that way. So actually some companies that travel all over the world are located in San Antonio within 5 miles of us. I'm not giving you their name. You can find them if you're interested. But forensics engineering, there's a whole society like American mechanical engineers and civil engineers. There's forensics engineers that go out and they study accidents. It's big money. And it's very important for lives and other things. Here's somebody, engineer, I'm sure, showing you where that valve was half open. And this right here, I'm sure they disconnected something because it wasn't working right, and they still needed it to work, right? Well, there's probably a part in there that broke. right? How many people drive around with a check engine light on? There's something broke in your car, but you're not going to fix it. It may be the brake system, and next time you're coming down the hill. Anyway, this part was bent, and that part was actually snapped on the low water cutoff controller. And so they probably bypassed it. And somebody may have bypassed it instead of figuring it out. And then they're showing you here the cutoff controller was stuck in the up position. I'm not certain. I didn't read the whole report, but they went in there and they had to figure it out. And then they said, oops, somebody didn't put the relay in right. Yep. So, okay, there was a great report. There's more out there if you want to look at it. Let's get back to thermodynamics. I think I covered all this disaster, right? They primarily were prisoner of war people. They were released from a local prisoner of war, and they went up. They were going from Memphis to Cairo, Illinois, and that was the capacity for the boat. How many people were loaded on? Standing room only. Seriously, no place to even sit or lay down, as I understand it. They made it 9 miles from Memphis toward their destination at 2 a.m. I'm sure that was worst for loss of life, because at 2 a.m. it's dark, the thing blows, you got fire, you got craziness, people jumping over. Once you jump over, you don't know what you land on, you don't know where you go, swirling, a lot of drowning or dying. Anyway, 1,800 approximately, they don't know how many. How do we improve the efficiency of the cycle then? Well, superheat it. Bring in more heat at high temperature and superheat it. That's logical. That'll make sense, right? From an entropy point of view. So you can solve a problem here. Let's say that I'm at 8 megapascal. That would be right around here. And instead of stopping right there, I bring it up to about 440 degrees C. So I brought in a lot more heat at high temperature. When I expand, I'll even have changed the quality, improved the quality at the outlet of the turbine, which is good. And then you can calculate the slight boost, but it's significant enough to do it in the thermal efficiency for this cycle. The Rankine cycle. It's still ideal, meaning the turbine's perfect, the pump is perfect, no irreversibilities, but you have now superheated vapor coming out of the boiler. I think we were able to see it on that diagram. Otherwise, I was going to try and show it here. So here's a plot. It's in Excel. I think I tried to talk about this last time. Did I not? Can I skip it? I covered it, okay? But the bottom line is boost the boiler pressure, drop the condenser pressure, and efficiency goes up. Spread them out. Spread them out. Now, we also want to do something to improve performance, and that would be to reheat. So reheat is where you take and you have 2 turbine stages. In the real power plant, they have 4, 5, 6 turbine stages, okay? But they'll stop and take the steam back to the boiler or steam generator to add more heat, but it won't be at that super high pressure that it came out originally. It'll be some intermediate pressure, but they'll reheat it, then they'll go back. So for this calculation, maybe it was 8 megapascal, expanded to 1 megapascal, then went back to the boiler to reheat back up to 440 degrees C. Then expand it down to 20 megapascal and continue with the pump and this is not supposed to be in here, sorry. Pump and then back, okay? That's an error in the diagram. Just after the pump, then feed into the steam water. There's no state 7, none of this. Let's take a look at what that looks like on this diagram. So we were out at around 440, 8 megapascal, right? Somewhere up in here. We expanded to 1 megapascal, right? Straight down, because it's ideal, until you get to the 1 megapascal line right around there. And I think the data showed a quality of around 98, 99% for state 2. So there's state 1, state 2. But then you reheat, so it comes out here and goes up, 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 all the way back to state 3, which is the same temperature of 440. And then expand again. And when you expand again, don't stop at 100 kPa, go down to 20 kPa, right around there. And then that was state 4, right? And the quality, jump back, at state 4, the quality is around 95, 96%, which looks reasonable on this plot of the TS diagram. Okay? But then you condense. There's state 5, true. And then state 6 is after the pump. So where is that on this diagram? That's probably the hardest one for students to place. Where is state 6? Where is it at? It is so close to 5, it's ridiculous. Right there. But it's on a different blue line. It's on the blue line associated with 8 MPa that comes down and goes over and then goes down. Okay? So the temperature is insignificantly less than a degree higher than state 5. But it's slightly different location. All right? Makes sense? So there you go. So you still have this inefficiency of bringing a lot of heat in before the water starts to boil. That brings up our next enhancement, and it's called regeneration. I have no idea why they call that. I would have called it something else. Feed water heater, preheat the feed water. All right? So this is what happens. What you want to do is you want what goes into the steam generator to be a lot warmer than what came out of the condenser. Because what's coming out of the condenser, essentially you add half a degree or 1 degree, and that's what's coming into the steam generator right now in our cycle. That's not good for performance. So what you'd like it to be, this to be a lot closer to the saturation temperature of the 8 megapascal or 10 megapascal, that high pressure. Okay, so how do you accomplish that without burning some external fuel? You want to use some internal heat source that's available to you. Well, you look and you say, let's do this. Take the two turbines and divert some of the flow after the first turbine stage that has a lot of heat content, maybe high temperature, but not a lot of potential to still do work, not a lot of exergy, and we'll use it to preheat the feed water. So the feed water coming into the steam generator or boiler is a lot hotter, so that the heat from our fuel doesn't come into the system at such a low temperature. It's coming in at a higher temperature. It's really going to improve performance. How much mass do you want to put this way? So you think about mass flow rate. You have some mass flow rate. So mass flow rate out the steam generator, right? That's what goes into the first turbine stage. That's what comes out the first turbine stage. But that's not what goes into the second turbine stage. That's going to be less, isn't it? Because you diverted some down to feed the open feed water heater. How much do you want to divert? At this point, this textbook uses the symbol y as a parameter. And y is a fraction. It's the mass flow rate that goes down to feed that open feed water heater divided by what came out of the steam generator, or they'll use this wording, what went into the first turbine stage. Have you looked at the homework? Have you read ahead in the textbook? Please do, right? This lecture will make a lot more sense to you. So they use this terminology, what goes into the first turbine stage, or what comes out of the steam generator, either one. Okay. So this is the fraction y that comes down. Well then, what is the fraction that goes to the second turbine stage? 1 minus y. So if 20% went down, 80% went over. it continued on. See that? So y may be 15%, then it's 85, 10%, then it's 90. Okay? What I do for the first time you go through a cycle like this is go to every one and say, is it y or 1 minus y? It's 1 minus y right there. All right? Now, let's follow this y. It's an open feed water heater. It mixes in. There's 2 inlets to this open feed water heater, and there's only 1 outlet, right? Isn't there only 1 outlet? And so you're following the mass fraction. 100% comes out of the steam generator. It splits. Y comes down. 1 minus y goes over to the second turbine. What comes out of the second turbine? 1 minus y. What comes out of the condenser? 1 minus y. That's 90% or 80%, whatever fraction that is. What comes out of the first pump? 1 minus y. 1 minus y joins with y in the open feed water heater. What comes out of the open feed water heater? 100% again. You're back to 100%. You're back to 100%. So I've got my mass fractions correct. I need to do that first. If you want, you can think about put m dot steam generator, m dot into the second turbine stage, mass flow rate into the second turbine stage, mass flow rate into the second turbine stage. You add that with the mass flow rate down to the open feed water heater, and you get mass flow rate out the steam generator, mass flow rate out the steam generator. So you either think mass flow rates or mass fractions. Okay. Now that I have introduced the concept y, I want to calculate what y should be. How am I going to find an equation to tell me what y is? Do a balance. What type of balance? A balance around the open feed water heater. I can do a mass balance. We just did it. Y, 1 minus y, 100% out. Energy balance. So the energy balance around that open feed water heater reads like this. We'll have the mass flow rate coming down to the open feed water heater, bringing with it the enthalpy at state 2. Isn't it the enthalpy at state 2, which is coming down there? The enthalpy at 2? That's a bad looking 2. Let's try and write that 2 again. There you go. Plus the mass flow rate that goes to the second turbine stage times the enthalpy at 5. Isn't that what's coming the other stream in? And it all goes out, the mass flow rate to the steam generator, times the enthalpy at 6. True? Do you like that equation? So let me pause. Does that equation look good? Everybody, if you agree, give me a thumbs up. I'm going to see a couple people that are still staring. I'm going to wait till their thumbs are up. You're good. Okay, I got your thumbs up. Are you good? Are you good? No? He's hesitant. You're too good? Over there. What are you doing? Looking at your phone? No phones. Look at the syllabus, please. All right? Attention toward me. Your thumbs up? Your thumbs up. Maybe you're bored, huh? You're good. You're good. Pardon? You're evaluating the junction. Like you did it. This is an energy balance, conservation of energy just for that control volume. I have 2 ins, 1 out. Look good? Anybody have me a question? Okay, if you divide over by m dot sg, m dot sg, m dot sg, guess what? This becomes that fraction 1. What does this fraction? 1 minus y. What is this? Y. True? So now you can solve for y, and you have y is equal to h6 minus h5 divided by h2 minus h5. That's the equation. It comes from an energy balance for that fraction that's diverted. Because if you're going to feed the pump, what do you want state 6 typically to be? H of F. H of F, what does F subscript indicate? Saturated liquid. You want to feed pumps optimally saturated liquid. So that's the highest energy content of 6 safe for that pump. So it's H of F at the pressure, whatever pressure 6 is. Okay? All right. Now the pressure at 6 is the same as the pressure at 5 is the same as the pressure at 2. that's an open feed water heater. They're just mixing. There's nothing in there to boost the pressure. So the pressure at 2, pressure at 5, pressure at 6 are the same. I'm out of time. Read the book, solve the problems, and we'll see you next time.